Okay, good morning, class.
Morning po, sir.
Ayan. Sige, tara. Tayo mag-aral. Mm-hmm. Teka, check ko na yung schedule natin kung ano yung mga ganap. Okay, reminders lang, no? So, Wednesday, holiday, which is nice. Tapos, yung next meeting natin sa lab would be December 7. Okay. Holiday ba yung December 8? Hindi ko alam kung holiday yung December 8 eh. Alam kung ginawa ni Bongbong na holiday ito eh. O sino man. Ayan, holiday nga. No? December 8, so wala tayong meeting nun. Okay, so we have 1, 2, 3, 4. December 17 tayo mag-exam. December 17. Last exam. Tapos December 14 yung final project. Tapos na tayo after 17. Ayos. Mag-exam din daw po kami sa 17 ng optics. O di dalawang exam kaya nyo yan. Anong oras kayo mag-exam? Kung sakali, kung sakaling sa 17 may exam na talaga kayo. Pwede tayo mag-exam sa 19. 19. Class time. Okay. Pwede po ba December? Hindi pwedeng December 21 kasi December 21 may yung mga tawag dito, lantern parade, ganyan. So, may mga naka-schedule na doon. Pati Christmas party nga ng CAS naka-schedule na ata ng December 21. So, syempre, hindi ako papahuli doon sa Christmas party na. Gusto ko naman manalo ng pera doon. Saan pera? Gusto ko manalo ng pera. May sync meetings pa din po until before exam. Yes, 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 yes. So, susulitin natin yung meetings. Remaining meetings. Okay, okay. Sige, sige. Within this week, dapat makapag-submit na kayo ng kung anong plano niyo sa final project. Bale, ibig sabihin, yung circuit diagram niyo. Tapos kung ano pa yung mga plano niyo, ibang plano niyo, paano gagawin yung mga bagay-bagay. How would you execute it? Okay? Okay. So, sige, mag-propose na lang ako on further details. Further details. Okay, okay. Sige, tara mag-ano tayo. Pwede po ba kami mag-consult through Zoom? Yes, 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 pwede. Pwede makapag-consult through Zoom. Okay. Kalimutan ko yung discuss ko. Okay. Okay, tara. Discuss tayo. Okay. Okay, good morning again. Di-discuss natin would be flow meters tsaka temperature sensors. Okay. Sa flow meters, ito yung mga ito yung mga devices natin that could measure blood flow. Okay, measure blood flow. And there's a lot of ways to do it. Una, meron tayo apat actually. May four popular examples tayo. Number one would be electromagnetic sensing. Tapos ito ay invasive. Number two, ultrasonic, ultrasound. Non-invasive. Three would be nuclear magnetic resonance. And then saka laser. Okay. So una, di-discuss ko ng intensive dito would be ultrasonic. Okay. Una, electromagnetic sensing ng flow meters. So paano tayo makakapag-sense ng ng blood flow? Okay. So yung blood flow, kunyari ito yung pink na lang yung vessel. Or ito yung vessel, no? Or ito yung cross-section ng vessel. Yung mga particles going to the right. Okay. Yung yung principle dito sa flow meters for electromagnetic sensing is that gagamit ka lang ng Faraday's law. Induction lang siya basically. So yung mga blood particles mo, if you can charge it, pag gumagalaw sila, nagpaproduce ka ng current. Okay? And that current produces magnetic field. Tama? Okay. So, ang gagawin mo is that kuha ka ng device para siyang ganito. So, i-hook mo siya dun sa blood vessel mo. Tapos, yung one side may wire ka to charge the blood. So maglalagay ka ng potential sa blood para magkaroon siya ng charges. And then the others could be an electromagnet. So pwede ka maglagay ng coils of wire para pag dumaloy na yung blood, makukuha mo ng madali yung magnetic field. Okay? And as you can see, no, as you can see, this is invasive kasi kailangan mo malabas yung ano. Kailangan mo mailabas yung blood vessel. Kailangan mo malabas yung blood vessel kasi iipit mo yung ano, iipit mo yung sensor mo. Kaya, bakit niya? Okay. Scary. Scary. Okay. Basically, ganun. Okay. No? Ano lang siya. Induction lang siya. Okay. Next, punta tayo sa ultrasound. Sa non-invasive invasive methods naman. So, magandang i-discuss yung mga non-invasive methods kasi they're popular. Nagiging-obsolete na yung mga invasive techniques natin. Siyempre, mas maganda yung mga walang dugo. Okay? So, kunyari, let's say there's may blood flow ulit, no? Going down. Okay? And meron tayong emitter receiver na naman. Emitter receiver. Tapos itong dalawang to, they produce ultrasound. Okay? Hindi, isa lang syempre yung nagre-receive. Binabombard niya yung binabombard niya yung blood vessels or yung skin actually. Okay, and then let's have an imaginary axis here. And then the angle is, let's say, theta. Okay. Okay. So yung angle between the orientation ng receiver transmitter. Tapos with respect to the blood flow. Okay, so anong goal natin? Anong goal natin dito is to make use of the sound. Diba? Okay. Pag sa sound, usually, and laser, ginagamit ay Doppler shift. So Doppler effect yung inaano natin. Tinitingnan natin. Okay? Okay. So ngayon, baka hindi nyo na maalala yung Doppler effect. So balikan natin. Okay. Ano yung general form ng Doppler? Ano? So gagamit tayo ng equation na readily made. No? General form ng Doppler effect is that meron kang listener. Ganito itsura niya. Okay, so let's define the variables. Yung mga L, sila yung listener. Tapos yung S, yung source. Okay, yung V dito, yung walang subscript, would be the speed of sound in that medium kung nasaan sila. Okay, and then, okay, yung VL would be the speed, yung speed nung yung velocity actually ng listener with respect to the tawag dito, with respect to the ground. And yung VS, yung speed ng source with respect to the ground. Ngayon, meron tayong sign convention here. If kapag yung L, yung listener ay going towards the source, then VL must be greater than 0 and VS must be greater than 0. Okay? Basta listener is going towards the speaker. Okay, let's apply. Okay. Kung tayo dito sa setup natin, meron kang ultrasound, meron kang source. Bale, ito yung source natin sa unang setup. Yung source natin, tapos yung listener would be the blood cells. Okay? The blood cells yung mga listener natin. So let's call the FL would be, gawin natin FB. Okay. Kasi yung listener natin would be the blood cells. B. Um, Tapos, let's call it V prime na lang. So, yung V prime, bakit V prime? Kasi yung speed of sound dito would be um, yung speed of sound sa loob ng sa loob ng vessel. Okay? Okay. Now, kailangan natin makuha yung yung VL at VS. Okay. So, yung VS, yung source natin is stationary. Steady lang tong yung transmitter mo. So, 0 yung VS. Yung VL, ay so 0. Lagay muna natin 0. No? Tapos yung VL, yung listener, bale yung velocity ng blood. Blood vessels, hindi blood. Would be, since ano yung nangyayari? Yung blood cells mo ay going towards the listener. Ay going towards the source. Sorry. Yung yung mga listeners mo. So, yung mga blood cells mo going towards the source. So, positive tayo. Positive tayo. Okay? However, meron siyang angle. So, kukunin mo lang yung portion nun. So, that would be V. V cosine theta. Okay? So, make sense na cosine theta, no? Kasi kapag nakatutok sa, nakatutok doon sa, naka-align yung blood vessels mo doon sa transducer mo, doon mo lang makukuha yung maximum effect nung Doppler shift. Okay, so make sense to. And then multiplied by F. Okay, so yung F natin would be yung natatanggap, which is this. Okay? Okay. So ngayon, meron tayong equation na ganito. Ito yung nakikita ng blood cells, no? Kapag binobombard mo siya ng sound waves. Okay. Now, kapag natamaan na siya ng sound waves, kapag natamaan na itong mga ng sound waves, it would reflect that sound wave. Tama? Kasi mag-vibrate din sila. Pa-vibrate din sila. Tapos, ibabalik niya yun dun sa receiver mo. Okay? Babalik niya dun sa receiver mo. Now, magpapalit na yung listener tsaka source. So, yung magiging source mo ngayon would be yung blood cells. Okay? Yung blood cells na yung magiging source mo ngayon. Tapos, ano i-emit nilang frequency? Itong frequency na tatanggap nila. Okay? So, let's call it F. FE. So, the emitted frequency, kaya FE na lang. Okay. May na-emit siyang frequency, FE. And that would be equal to, gagamitin lang natin yung yung formula natin for the Doppler shift. Okay? Okay. So ano ngayon yung mag-zero out? Yung mag-zero out would be yung listener. Okay, yung listener, zero na siya ngayon. Kasi yung listener natin would be the receiver, yung device. So V prime plus 0. Then the denominator would be something else. Now, yung convention natin, listener going towards source. Ngayon, baliktad na. Yung source gumagalaw, yung listener steady. Tapos napansin naman natin na yung source natin, yung blood cells is going towards the device or to the listener. Therefore, negative yung sign ng nandito natin. So explicitly, let's put that negative b cosine theta. So cosine theta pa rin kasi same orientation naman yung ginawa natin. Okay? So we have these two equations. And then syempre, ang gusto natin makita itong shift na to, no? Gusto natin makita itong shift na to. So we would actually need we'd actually need to remove yung original frequency from here. So Fe minus F. Let's call this delta F or yung Doppler shift mo. So we have yung Fe natin would be V prime minus VB cosine theta times FB. Tapos plug in na natin si FB para ano tayo. So bilis. So on the second factor, magiging V prime yung denominator, tama? Tapos sa numerator, V prime plus VB cosine theta. Okay, tama. Tapos multiplied by F. So this is the first term. Ano yung second term natin? Minus F. Okay. So now we have something like this. Let's factor out the F. V prime cancels out. Tapos, ano yung nagtira? V prime plus V cosine theta. Denominator is V prime minus VB cosine theta. 10 minus 1. Okay? Kasi pinactor out natin yung F. Okay. Next ay pagsamahin natin para mag-cancel yung mga dapat na mag-cancel. So, V prime plus VB cosine theta minus V prime plus VB cosine theta. Okay? Naging positive, no? Kasi negative sign times negative sign, you have positive sign. And then, this cancels out. You're left with F times 2 VB cosine theta. And then, denominator would be V prime minus VB cosine theta. Okay? Now, the speed of sound is definitely faster than the speed of blood cells. Kasi magulat ka kung simbilis ng speed of sound yung dugo mo. So we have an approximation yung denominator will be dominated by the speed of sound in the vessels, in the blood. So we actually have 2F VB cosine theta divided by V time. Okay? Okay. So what we actually need is VB, which is isolate lang natin. And that would give me delta F V prime divided by 2F cosine theta. Tama ba? Tama, di ba? Okay. Tama naman yung math. Okay? So, ganyan natin nakukuha yung speed of blood or yung flow ng dugo, no? Flow ng dugo dun sa vessels natin. Using Doppler shift. So, yung delta F, madali siya makuha. Basically, yung delta F mo would be taking the difference between dun sa binibigay mo tsaka sa natatanggap mo. Okay? And then you can design your transducer so that makukuha mo yung desired theta mo. Okay. Desired theta. So pwede kang gumawa ng gumawa ka ng something like this. So magkadikit halos yung transmitter then receiver tapos i-encase mo siya i-encase mo to sa something na diagonal na ganyan. Okay? Okay. So para maintained yung angle kapag nilagay mo siya sa balat ng tao. Okay? Amazing, amazing. So ayan. Okay? Sana na-review ko ng Doppler shift. Similarly, yung pang-apat, ganun din. Yung laser na method. So laser na Doppler shift. Ang difference lang nila would be ito ay gagamit ng light. Okay? Light yung gagamitin niya. Imbis na sound. Tapos yung nuclear magnetic resonance, ano natin gagawin to? Yung nuclear magnetic resonance, hindi natin in-depth gagawin. But let's have a view on how it works. Okay, kunyari may kamay ka, no? May limb. Close thumbs na lang. Yung gagawin dyan is that i-magnetize yung upper limb mo. Okay? Bombard na malakas na magnetic field. Tapos syempre, mag-a-align yung mga hydrogen atoms mo sa blood mo kasi yung blood natin ay around 80% water. So maraming hydrogen and mag-a-align yun sa since polarized naman yung water molecules. Mag-a-align siya sa magnetic field. And then papasok mo to sa other device that would check yung orientation nung tawag dito. Nung mga molecules. check niyo yung orientation ng molecules. Basically, with NMR, pati with MRI, magnetic resonance imaging, kailangan mo makuha dito is yung amount, yung precession nila. So, yung angular velocity. Okay, ito ay 2. Pangit purple. 2 pi times yung velocity. So, ito ay angular velocity, di ba? Okay. Tapos, equal to sa gyromagnetic ratio times yung nilagay mong magnetic field. Okay. Now, syempre yung V mo dito would be the linear velocity nung pag-process nung tawag dito, molecules. So, drawing tayo ng molecule. Di ba mukhang Mickey Mouse yung water molecules? Kung pag nag-align siya ng ganyan, nag-align siya with respect to the magnetic field. At some point, babalik siya sa other orientation niya. Okay. That's this. Now, yung time to do this, yung time from this orientation to this orientation, may average time siya, no? May average time siya. Now, syempre, may velocity din yun. Yung pag-rotate niya to this. And kapag may blood flow ka, yung rotation, yung movement na yan would be extended. Diba? Kasi may dumadaloy ng dugo. So ito, nakikita at other frames of reference. Nag-elongate yung motion niya. So ganun nakikita yung blood flow. But I think this is too much of a magastos yung ganitong model. Kasi kailangan mo ng powerful magnetic fields. And then yung application lang nito would be on the limbs. Kasi dun medyo linear yung blood flow. At other parts of the body, na sa torso, hindi mo na magagawa to kasi random almost random yung blood flow mo sa katawan. Okay. Now let's talk about temperature sensors. Yung pinakamadali gumawa ay temperature sensor. Temperature. So usually kasi bakit siya madali? Kasi yung conductivity ng mga bagay-bagay, nagva-vary with temperature. So anything that is a conductor, kahit anong bagay actually, di ba? Nagbabago yung resistance kapag iniinit siya. Kahit insulator pa yan, nagbabago yung niya. Nagbabago yung conductance and resistance niya. Okay? So, ang usual na ginagamit na is if you have metals, meron kang formula na ganito. Okay, so yung resistance can be a function of this one. So yung T dito would be temperature. R naught would be the resistance of the metal at 0 degrees Celsius. Alpha is yung yung properties yung properties ng material. Wait, let me check kung ano yung exact what we call it. Ito ay ito ay, wait lang ah. Okay. Pangit naman ang tawag sa kanya. So again, R naught is yung resistance. Sulat natin. 0 degrees Celsius. And then alpha would be temperature coefficient. Of resistivity. Okay. Okay. Ito medyo fun pa siya kasi ano, linear siya. Okay, linear. So, sama na lang siya. Hindi siya quadratic, di ba? Okay, so madali pa siya. So, ito lang yung ano natin. Ito lang yung point natin. Now, syempre, madaling gumawa ng sensor design ito. Okay. Of course, you can build an easy circuit such as this. Okay? So, ito kunyari yung ano mo, no? Yung resistor mo na nagbabago ng ano, madaling magbago ng resistance with respect to temperature. Definitely, when this resistor changes, resistance value changes, magbabago yung ma-measure mong voltage dito. Okay? Okay. However, itong circuit na ganito, very dependent siya doon sa source mo. Okay? So, kailangan malaman ko ni source mo para malaman mo kung ano yung nagbago. Okay? Pangit pala yung gantong circuit kasi constant yung voltage dito. Dalawang resistor gamitin natin. Okay, so dalawa. So yung isa basis lang. Okay, so pag nagbago yung temperature nito, magbabago yung resistance niya, magbabago yung voltage na makukuha mo. Okay? However, this is, sabi ko nga, ano siya, voltage dependent ito kasi, let's call this R T, and then this is R. By voltage divider, yung circuit mo would be, let's call it T times. V prime mo will be V. Ay, ito ako nag-equal ulit. RT divided by R plus RT. Okay? Okay, so very voltage dependent siya. Hindi ka basta-basta makakapag-measure lang. Tapos yun na. Okay, maganda na kapag yung circuit mo direct ka na, no? Yung may measure ka na tapos ka na in life. Okay, so paano tayo gawa ng ganyan? Paano tayo gawa ng ganyan? Sa mga gantong sa mga resistance varying parameters, madaling gumamit ng Wheatstone bridge. Okay, naalala niyo pa ba yung Wheatstone bridge? Basically, yung ganito itsura. Ay, mabra. Okay. Recall natin, balikan na lang natin yung lesson natin about this. So we have something like this, a Wheatstone bridge. Then napansin natin, para gawin to, di ba, kailangan mo ng Thevenin equivalent circuit mo kay R5. Okay, kasi yun yung mahirap na part na kunin. So yung R5, tatanggalin mo siya. So it becomes like this. And then you do the process of simplifying it, and then you get VTH and RTH, which are these equations. Okay? And as you can see, sa VTH, meron siyang formula na ganito. And looking at this, you can zero this out by an appropriate choice of R1, R2, and R1, R2, and R3, and R4. Okay? So sa choice mo ng mga resistors na to, kaya mo siyang gawing zero. And that means na pag nag-zero to, walang dadaloy na current sa R5. Okay? Walang dadaloy na current sa R5. Okay? And ano yung condition na yun para walang dumaloy na current sa R5? Ito, kailangan mo zero. So, equal mo lang sila. Ito siya. Okay. Kapag maintained yung ratio ng R3 sa R1 tsaka sa R4 to R2, and you have this relation, walang dadaloy na current sa R5. So, anong point ko? So with this, you can actually have, ito yung temperature dependent resistor mo. R. Okay. So suppose that R is RT at room temp. No? Then, walang dadaloy ng current dun sa gitna at room temperature kasi R over R is equal to RT over R. And since RT is equal to R at room temperature, this is also equal to R over R. And you are satisfied with the ratios of the two. Okay. Now, ang gagawin mo, pwede mong palitan itong nasa gitna ng ammeter. Putulin mo na siya, gawin mo ammeter. Gawin mo ammeter. Okay. So, pag ginawa mo siyang ammeter, pag binago mo yung resistance nito, definitely may magpo-flow somewhere in between. Okay. So, ayan. Mas madali itong circuit na to kasi naka-zero siya at room temperature. Or you can choose it to be other things as well. Okay. So, may freedom ka to set your zero here by just choosing the values of R or whatever ratios you want. Galing, di ba? So, ayun yung purpose ng Wheatstone Bridge. Pang balance siya ng mga bagay-bagay. Okay? And then, meron tayong tinatawag na thermocouples. Thermocouples ay two kinds of metals joined together. Okay. Now, napansin ng isang scientist no, na kapag ininit mo yung isang side, so meron kang junction ng metals, di ba? Meron kang junction ng metals. Sorry. Meron kang junction ng metals, so yun yung thermocouple mo. Pag ininit mo yung one side, napansin nung gumawa nito, nagpo-produce yan actually ng different potential. So, ano nangyayari? Basically, para siya nagiging capacitor. Kuwari ito yung thermocouple. Kunyari, magkadikit sila. Now, kapag naglagay ka ng heat to the other side, nagiging excited yung electrons and some of it tumataas ng energy level. So, apparently, nagmumukha siyang mas maraming charge kaysa dun sa kabila. Okay? And then kapag meron ka nangyayaring ganun difference in the amount of charges between two conductors, ang nangyayari ay magkakaroon ka ng gradient in potential. Kapag may gradient in potential ka, of current, and so on and so forth. Okay, so napansin niya that the potential is a function of temperature when it comes to thermocouples. Okay? Tama po ba na yung resistor na ginagamit natin, nagbabago ng resistance with temperature? Yes, nagbabago sila ng resistance with respect to one. Pero yung mga resistors natin, usually, they are ceramic. So, ano nila, very resistant to heat. Unless na lang mababa yung resistance nila. Okay? So, yes, nagbabago yung nagbabago yung resistance nun. So specifically, meron tayong mga bakal na ginagamit for temperature measurement. Okay? Kaya po ba malakas aircon sa lab natin or hindi naman? Malakas aircon natin kasi mainit. Pero mas okay mag-work ng malamig na electronics. Okay? Para ideal yung nila. Ideal yung paggana nila. Okay, so ayan, thermocouples. And then, meron pa last na kind. I think thermistor ang tawag, thermistors. Thermistors. Oxides yung gamit nila. Metal oxides. Okay? And then, ito ay yung resistance nito ay somewhat ganito yung itsura niya. Exponential. Okay, exponential yung So A and B ay constants. Constants sila na hindi ko alam. Na nakadepende sa nakadepende siya sa properties ng materials. Hindi ko alam. Okay, depende siya sa given material. Okay? So kanina linear, tapos ngayon sa thermistors exponential. Okay? Okay. So kailan mo gagamitin yung mga different kinds? Depende sa application. Okay. May mga resistor na may mga material that wouldn't be effective at high temperatures. Okay. Pag high temperatures na kasi, ang mangyayari ay magkakaroon ka ng hysteresis. Hysteresis. Nakalimutan ko yung spelling. Search ko na lang. Wait. Para sigurado. Tama naman pala yung spelling ko. Hysteresis. Basically, pag nagkaroon ka ng hysteresis, ibig sabihin yung material mo hindi na nagpo-follow ng Ohm's law. Okay? So, kunyari, at high temperatures, hindi na magiging linear yung relationship ng V to IR. Okay? So, you wouldn't want that. You don't want that. Kaya merong specific na temperature sensor for its application. Okay? Kung body temperature lang, merong mga specific na pwede na. Okay? Yung mga thermocouples, usually ginagamit siya sa industry applications. Yung mga sensors sa mga induction cooker, mga ganyan. Tapos kapag, alam ko yung thermistors for a more, for a more sensitive applications. Ibig sabihin, mas gusto mo na for a single centigrade increase, ilan yung resistance na magbabago. Okay. So, mas siya, mas sensitive. Mas makakapili ka ng resistance that mas malaki yung resistance that corresponds to a smaller temperature. Okay. Mas madali mo makikita yung change in temperature. Okay. Ganong applications. And of course, yung cost. Lagi magmamatter yung cost. Diba? Kasi some of these, mas madali ma-procure. Yung iba, tulad ng thermistors, mas mahirap siya. Kaysa dito sa normal na linear relationship na resistances. Okay. You might wonder na bakit sa biomedical instrumentation, ang daming ways to do it. Ang daming, parang ang variable ng mga pinaggagawa natin in life. Kasi it is, no? Kapag nag-work kayo sa mga kumpanya na nagmamanufacture ng mga bagay-bagay, lalo sa mga biomedical instrumentation, yung way of doing it is not universal. Pagalingan siya with respect to a different company. Okay? Kapag kunyari sa oximetry mo, if you have other ways to do it, then you may do so. Kuwari ito, hindi mo sinunod to, okay lang. Okay lang if you nakaisip ka ng other mathematical relationship that would produce better results, then it would be okay. Okay. Kung much better nga siya kapag tinry sa clinical trials. Then, ayun. So, itong mga diniscuss ko dito, lang siya, mga existing ways to do it. Okay? So, sa measurement analysis, pansin nyo parang bakit wala siyang defined way to do it. Kasi, ayun nga, pagalingan siya when it comes to the corporate aspect. Bakit siya walang So this one is this way of doing it is just one example. And kunyari sa ECG, basically ECG. Ang ECG mo ay para ka lang nagme-measure ng potential across the body. Okay, so parang kinakabit mo lang yung katawan sa oscilloscope. Ganun lang yung basic niya. Ganun lang yung basic way of niya. But then again, hindi naman pwedeng ganun lang, no? Hindi lang pwedeng oscilloscope lang tapos titingnan mo yung heartbeat doon. Masyado siyang mabagal. So you want that your ECG is fast, meaning that kunyari meron kang tatlong probes. So, 'di ba, tatlong probes usually yung minimum. Ilalagay mo sa magkabilang kamay tapos isa sa paa. Okay? And then those are voltage probes tapos may mariread yun, no? So mapupunta siya sa isang computer. Okay, at the computer, so dumarating yung data sa'yo. Something like that. So ito ay voltage with respect to time. Okay, so yung data sa'yo dumadating unti-unti. Dumadating siya sa'yo unti-unti. So itong buong data na to, it doesn't come to you like this. So unti-unti siyang darating sa'yo. So ngayon may different algorithms, no? May different algorithms kung saan kung saan nade-detect agad yung yung mga bagay-bagay related to your heart kapag ginamit mo yun. Okay, so kunyari sabi ko nga hindi mo naman makukuha yung buong waveform. Or if you do, kuwari hinintay mo yung 3 heartbeat, then yung device mo would be late. Okay, pangit siya. So gusto ng mga tao is real time. Okay, so kunyari nakaabot ka sa 3 beats bago ka nakapag-analysis ng mga bagay-bagay. So, talo ka na sa market. Kung gusto natin, nag-a-analyze ka na pagdating pa lang sa'yo ng data. So, kunyari, pagdating sa'yo ng data dito, ay, tagal dumating ng heartbeat, baka may problema sa heart to. Ay, ang tagal umakyat sa T-wave. Ay, ang erratic ng QRS complex. So, may mga ganong algorithms to detect arrhythmia and whatever heart complications that you may have. Okay. So, syempre, hindi available sa atin yun dahil mga patented work sila. Pero basically, ganun sa medical setting. May sinusunod na algorithm yung device. So, now, kapag nagtrabaho kayo in the future, if you are to develop this, improve this kind of algorithms of detecting anomalies in the heartbeat, then marami siyang pera. Okay. So maraming pera sa electronics. Okay. Do you have any questions? Sir, paano nag-work yung mga temperature guns? Tsaka temperature sensor sa malls na tinatapat? Doppler shift. Pwedeng Doppler shift din. Pero yung madaling way ay reflective way lang. So, yung temperature kasi ay madali makita through infrared. So, a higher intensity of infrared given of the body means that you are hotter. So, pag binombard ka ng infrared, tapos mas marami ka na reflect, ibig sabihin, mas mainit ka. Okay? So, yun nandun sa mga temperature guns. They usually have emitter tsaka receiver. Dalawang diodes yun. Isa magbo-bombard sa'yo, tapos babalik. Okay, sige. This ends the lessons for today. May mga tanong pa ba? Okay, kung wala na or kung meron man, i-send nyo na lang sa Canvas or sa email. And yan, dismiss na. Wait, may tanong pa pala. Makahingi na recording. Ay, okay, yung recording. Sorry, hindi ko pa pala na-upload. I was busy nung weekend. Okay, sige, upload ko na now after this meet. Okay, thank you for reminding. And teka mo check ako attendance. Okay, so sino yung gusto mag-on cam na.